Hey, welcome back everybody. So today we essentially want to prove two cousin results from group theory and linear algebra. Number one says, well, if G and H are groups and F is a homomorphism and we have a trivial kernel, then we're guaranteed that F is injective or one-to-one. Number two says if V and W are vector spaces and T is a linear transformation, and again we have a trivial kernel, then we're guaranteed that T is injective or one-to-one. All right, so let's go with the group theory proof first. And of course, we want to assume that G and H are groups. And, well, also, this map F from G into H is a homomorphism. And let's suppose we have a trivial kernel. And so we want to show that F is injective. So you should be thinking about all the properties of homomorphisms and also think about how do we prove that a function is injective. So that's going to be absolutely key. So we want to pick two elements in G. And so let's maybe assume that the image of G1 equals the image of G2, where, well, G1 and G2 are elements of the group G. And we're going to introduce a helpful quantity and keep in mind the properties of homomorphisms. So I'm going to say consider f of G1, G2 inverse. Well, since f is a homomorphism, so over the equals I'm going to write hom. So since f is a homomorphism, we have f of G1 times f of G2 inverses, or inverse rather. Okay, so now we want to think about a property of homomorphisms, that a homomorphism will send an inverse element to the inverse, right? So this will map to f of G2 inverse. So I'm going to say by previous result, this is the same thing as f of G1 times f of G2 inverse. Okay, and that's a nice property of homomorphisms. But now we want to recall something, right? We want to recall something. So remember we made the assumption that f of G1 is equal to f of G2. So that means we can replace this. So we can replace this with f of G1 since they're equal. So by our assumption, this is f of G1 times f of G1 inverse. But when I multiply inverses, I get the identity. But let's note something. So what does that tell me? So that means that this quantity is in the kernel, right? That's the important part here. So since the image of this was equal to the identity element, that guarantees just by definition of kernel that this is an element in the kernel. So maybe I'll note this. So by definition of kernel, G1, G2 inverse is in the kernel of F. But think about that. Our kernel is trivial. There's only one element in there. So if that element is in the kernel, and the kernel only contains one element, then this must be equal to this, right? Since, again, we have a trivial kernel. And so thus, G1, G2 inverse is equal to our identity element. Well, keep in mind what we're trying to prove. We're trying to prove that F is injective, right? That's our goal. So if we do this successfully, we would like to show that G1 is equal to G2. So let's compute a right multiplication. So let's multiply both sides on the right by G2. Okay, so we know that this is the identity element. So we have G1 times the identity is equal to the identity times G2. And therefore, we have G1 is equal to G2. Therefore, F is injective. All right, so we've established our result for group theory. Our next goal is to establish our result for linear algebra. So let's take a moment and remind ourselves what that result was. So taking off my group theory hat, putting on my linear algebra hat. You should see these hats, really. Okay, so this is what we want to work with now. So we're working with vector spaces, properties of linear transformations, and we're keeping the definition of injectivity in mind. All right, let's do this. Let's prove it. So let's say let V and W be, well, vector spaces. And, well, T from V into W be a linear transformation. And again, we want to assume that the kernel of T is trivial. Okay, so we want to show that T is injective, or one-to-one. All right, so let's suppose that T of U is equal to T of V. Our goal is to show that U equals V. And that's for U and V in V. Okay, so let's subtract T of V from both sides and then keep in mind properties of linear transformations. So if I subtract T of V from both sides, I've got the following. So T of U minus T of V is equal to the 0 vector. But by properties of linear transformations, we have the following. Well, that's pretty nice. So what does that tell me about this element? Well, since the image of this is equal to 0, that guarantees that this is in the kernel, right? Just by definition of kernel. So we must have, so I'll say by definition of kernel, that u minus v is in the kernel of t. But the kernel of t only has one element, right? The kernel of t is trivial, right? The kernel of t in this case is equal to, well, the set containing the zero vector. And so thus, u minus v is equal to the zero vector. And this implies that u is equal to v. And therefore t is injective.